Our focus in this video will be Euler's formula. Euler's formula says the following: if G is with a vertex set of V and an edge set of E is a connected planar graph, and R is the set of regions in a planar representation, then we have the formula: the number of vertices minus the number of edges plus the number of regions is equal to 2, where we're using this idea with the bars on either side of the set, as we have before, to be the number of elements in V, right? So the elements in V here are vertices, so that counts the number of vertices. So one way you could actually write this out in words would be to say the number of vertices. By the way, those are the zero-dimensional objects, minus the number of edges, the one-dimensional objects, plus the number of regions, the two-dimensional objects, is equal to 2, right? So that's an equivalent version in words. So the basic ideas, there's actually two things that we'll do in the theorem, and one is to make use of the fact that a graph can be built up in steps, a connected graph. So I'll scroll up here and say this: a connected graph can be constructed starting with a single vertex just a single vertex, and at each step adding a vertex and edge, which I might indicate like that, to an existing vertex so it adds a pendant, or adding an edge, just like so. I'll put two open circles there to indicate that we're not adding any more vertices to existing vertices in the graph. Now, actually showing that is in itself a little bit of an induction, so that it shows that if you have a graph of n-1 edges, then the graph that you want with n edges can be created from such a graph. If it's true in a graph of n-1 edges, all such graphs, then it will be true for all such graphs of n edges. The way that you can actually prove that is by saying, well, if you have a graph of n edges, it may have a pendant vertex. Okay, take away that pendant vertex and its edge, and you have a graph with n-1 edges, and you're assuming that it can be built up in this way. So all you have to do now is add that edge back in, and the graph of n edges can be built that way. And the other case is similar. If it does not have a pendant, then in fact the longest trail in the graph will have to wrap back on itself, because there's no pendant vertex, creating a circuit which does not disconnect the graph if you remove an edge. And there again, you're back down to n-1 edges, and assuming all graphs of n-1 edges can be built up as I have described, then by adding just that edge back in, you've created the desired graph of n edges, and it has been can be built up then with these steps. It's pretty intuitively obvious anyway. So what I verbalize there without writing is a little bit more of the technical way of looking at it. So we're going to use that fact here in an induction here as well. We'll assume that the formula holds when we have n edges. Oh, let's first do a start here. So the basic proof is to look at the a basis case. In the basis case, with a single vertex, if G has no edges, so 0 edges, this is the case n equals 0, then we have V would be one vertex, a single vertex case. E has no edges, and how many regions are there? Well, let me sketch this so we can view it. So here's our graph right here, just that one vertex, and there is one unbounded region in that planar representation. So we have V and R each has one element, and it's clear that the formula holds there. We'll have V, number of things in V minus number of things in E plus number of things in R is 1 minus 0 plus 1 is 2, right? So now let's assume it's true for a graph, a connected planar graph with n edges. Assume the formula holds for all connected planar graphs with n vertices and let G be 1. By that I mean connected planar graph with n plus 1 vertices. So let's call that Gn plus 1, and let's let Gn be the graph Gn plus 1 arises from by adding an edge vertex or just an edge. Okay, so we know it's true for Gn by our assumption, our induction assumption, and so we have for Gn, we have Vn minus number of things in Vn minus number of things in En plus number of regions is equal to 2. And we're going to consider what happens for Gn plus 1. For Gn plus 1, the cases are, case 1 will add the edge vertex pair. So that would say that Vn plus 1 has the same number of elements of Vn plus 1 because we added this vertex right here. And then we'll have that the number of edges in this case also increased by 1, right? So how about the number of regions? Did the number of regions also increase by 1 or not? Well, if you imagine what the graph looks like in this case, we've got some sort of graph going on here, and we added to an existing vertex this new edge vertex pair, but this is a pendant. It didn't change the number of regions, so the number of regions stayed the same. Whoops, I was going to add one there. And so what we have is that then the number of things in the new vertex set minus the number of things in the new edge set plus the number of things in the new region set is equal to the number of things in the old vertex set plus 1 minus the number of things in the old edge set plus 1 plus the number of things in the old region set. If the ones cancel, yeah, that one cancels with that one, And so we already knew this was 2 before. The formula held for Gn, so it holds again. In the other case,